In our initial video about the data link layer, we promised to talk about 3 themes. The one theme was error control, which we've just concluded. What remains to talk about is data delineation and media access control or contention control. Today's video will be about data delineation, and in it we will encounter quite a couple of examples of data link protocols. It's rather important to take note of those protocols as well as of the techniques that they use. Data delineation, as we already indicated, is used to frame your packets, or technically on layer 2, not the packets, the frames. So what we need to look at are 2 things. The one is, how do you indicate that a frame starts here and ends there? Thinking about it slightly differently. On the physical medium, you may have an electric current or voltage level or whatever is used to represent data, and that may remain low, and that may mean a lot of zeros, or it may simply mean that nothing's going on. So somehow you need to know, where do I start and interpret what follows, and where do I end, and what is just accidentally on the physical line. So on the one hand, we have to think about framing. Framing in the sense of, where does something begin and where does it end? There are 2 options. The one is to use some sort of a, let's call it a mark for the time being, to say that this is the start of a frame. And then at the end, we have 2 options. We can have another mark. It may be different, it may be the same, to say this is the end. But as an alternative to that, we can also have something in the frame that tells us how long the thing will be. In other words, some sort of a length field. And if we know how long it is, then we don't have to mark the end. We can just receive so many bits or so many bytes, and we know that we've received everything we should have received. In terms of the frame itself, the frame probably consists of fields, and we also need to determine how those fields, we need to distinguish where they are. We need to identify where they are. And there are a couple of options that exist for those. So in terms of fields, we have known field lengths. So I know that this field is so long and that field is so. So if I get a certain sequence of bytes, I can simply say I know the first 2 indicate the source address and the next 2 indicate the destination address, and so on. So that's one option. Another option is, again, some sort of a mark option to say that this is the start of this field and this is the end of the field. And here we can also have a length, some sort of a field that tells us how long another field will be. So in a given protocol, we may use either the same or different mechanisms. Very often you will see that we use some sort of a mark, let's say to begin and to end a frame, but then we will use known field lengths on the inside to specify so that we know exactly where each field begins and ends. Let's look at a couple of examples. Our very first example of a layer 2 protocol is BiSync or BSC. full name, the binary synchronous protocol. This is a very old protocol. It predates thinking about level 2 or layer 2 in the way we do nowadays. In fact, it comes from the days of punched cards. And what you wanted to transmit when you were using punched cards were basically ASCII characters. Now, if you think back to what we saw when we looked at the ASCII table a while ago, there were some control characters included in the ASCII table. They included things like SOH, that was the start of header, and something like STX, the start of the text, and EOT, the end of transmission. So what you could do there was to include these special characters, which will never be mistaken for alphabetic characters, and you could delineate your packet, frame your packet, by saying this is where it starts, by using a special start character, and say even delineate the fields. For example, by saying this is the start of the header and this is the start of the text or the actual message. As long as you want to transmit ASCII characters, that is fine. It works very well. But now suppose that you want to transmit, let's say, a JPEG image. That JPEG image has nothing to do with characters whatsoever. And every byte is just some bit pattern. And that bit pattern may, right in the middle of your image, look like something that happens to have the same value as end of transmission. And the moment when the receiving host sees that, it says, okay, that's the end of your transmission. I'm cutting you off. And there's no way that you can get your picture through the network because it has these binary values that look like character codes. The problem that this introduces is known as the transparency problem. Transparency in this context means I should be able to send anything via the data link layer. I should not have to worry whether it clashes with any specific value, whether it happens to, by accident, look like an EOT character, and so on. And in what follows in the other protocols, you will see that in each case we will find some solution for the transparency problem. In Bisync, they later modified the protocol to enable you to transmit anything, so they added transparency. They did it in a very, very clumsy way. It's clearly something that was retrofitted, and we could spend the next half an hour to talk about it and discuss its merits. But the bottom line is Bisync is old. No one uses Bisync, and the only reason why we really mentioned it was to introduce the problem of transparency. And beyond that, there's very little that you need to know about Bisync. Our next example of a layer 2 protocol is hdlc, Synchronous Data Link Control Protocol. This is an IBM protocol, and after it was defined, it was also accepted in a sense by the ISO, and they defined a protocol that was heavily based on it, and they called it hdlc, the High-Level Data Link Control Protocol. In defining hdlc, they added a couple of features and they removed a couple of features, but none of that's really important for our purposes, so we can deem them to be the same protocol for the purpose of this discussion. The way in which data is delineated is by using what is known as a flag. And a flag has the bit pattern 0 and then 1, 2, 3, 4, 5, 6 ones, and then a 0. This raises an obvious question. What if that pattern occurs inside your data? Just before proceeding, it's perhaps worth noting that the flag marks both the start and the end of the data frame that you're sending. So on both sides, it's used to delineate this frame. So back to the question, what if that pattern happens to occur in your data? Answer is something that is called bit stuffing. And it works as follows. The algorithm says, while you're transmitting the flag, transmit it just in its standard form, exactly like it looks there. But while you're transmitting data, if you ever find yourself in a position where you have transmitted a sequence of 5 ones, transmit a 0. So clearly, if in your data you have something that looks like a flag, so 1, 2, 3, 4, 5, 6 ones and a 0, and you send that out, so this is now part of the data, so it's between 2 flags, then at that position, after the 5 ones, it will insert a 0, so it would be 0 and then 1, 2, 3, 4, 5 ones, the inserted 0, then the remaining 1 and 0 that we had from the original data pattern. One of the things that people very often miss here, suppose I want to transmit data that looks as follows. It's a 0 and then 1, 2, 3, 4, 5 ones and a 0. Now that doesn't look like a flag. It's not going to cause any confusion whatsoever. So a lot of people will want to transmit that just as is. But remember what the algorithm says. After 5 ones, insert a 0. So that will be transmitted as a 0 and then 1, 2, 3, 4, 5 ones, and then the inserted 0 and then the 0 in the original data. So just to get back to the terminology, the bit stuffing, that 0 there will be stuffed in. Why? The reason is on the receiving end, if you are receiving a sequence of 5 ones followed by a 0, then you know that that 0 has been inserted and you can remove it and not give it up to the higher layers. So in both of these cases, the recipient will know that that 0 has been stuffed and it will just remove it before it passes it to the higher layer. If we transmitted this pattern in its form in which we had it with 1, 2, 3, 4, 5 ones and a 0 because it wouldn't cause any problems, the recipient will not know whether that 0 was in the original data or not, whether it was stuffed in there, and it will probably remove it and we will end up with something that differs from the original value. hdlc and hdlc use known field lengths inside the frame, so it knows exactly how long every part of the frame will be, and therefore it doesn't need to delineate them in any particular way. More specifically, everything in the header has a known length. The payload can have a varying length, but it will be terminated by the flag at the end. Our next example is arguably one of the most popular layer 2 protocols on the network today. It is Ethernet. Ethernet has a long history and there are different versions of Ethernet. So when we look at packet formats of Ethernet in a short while, you will see that there are differences. For our purposes, we can ignore most of those differences with perhaps one exception that we will get to a little bit later. One thing to note here is that a version of Ethernet was standardized by the IEEE. We had a couple of protocols that were being used, especially on local area networks on layer 2, and there was some need for standardization. The IEEE didn't look at the various options and say, okay, this is the one that we pick and we're going to standardize it. They rather looked at Ethernet and they standardized it as IEEE 802.3. They also looked at a different protocol that we will encounter very, very soon, the token ring protocol, and they standardized that as 802.5. And between these two, there was another interesting one that they standardized as 802.4. And if you've looked at Wi-Fi at all, then you probably know that 802.11 is Wi-Fi. We're not going to talk about those. We're just highlighting the fact that as far as Ethernet is concerned, when we talk about 802.3, we are talking about Ethernet and vice versa. We deem the two to be more or less the same. Differences are minor, but there are variants of Ethernet, and they are not variants of the standardized protocol. Before we start talking about data delineation in Ethernet, we have to remind you of something that you probably already know. Ethernet is designed to be used on a bus. So what that means is that you'd have a piece of cable, and the various nodes on this cable will plug into the node. At some point, we will show you how in the olden days, vampire clamps were used to bite into this so that they literally could be attached anywhere on this bus. So what this means is when a node speaks, everyone else is able to listen to what is being said on the node. The mechanism that Ethernet uses for data delineation works as follows. It uses 64 bits that have a sequence as follows: 1 0 1 0 1 0 1 0, and so on. Well, actually, that's not the entire truth, because the very last 2 bits in the sequence would have been 1 0, and it becomes 1 1. So at the end, bit number 64, if you were using the pattern 1 0 1 0, should have been a 0, but it's a 1. Now, why? All the other stations that are plugged into this bus will hear when someone starts to talk. They sort of say 1 0 1 0 1 0, and the other stations are not only seeing that there's activity on the bus, but they're also seeing, or they're also getting this rhythm, this 1 0 1 0, and they can synchronize themselves. They can set their clocks to say, that's the start of the bit, that's the end of the bit, that's the start of the bit, that's the end of the bit. So they may not even hear the first couple of bits in the sequence, but as it goes up and down, up and down, up and down, at some point it will become aware of that. And then the moment that it sees the 1 1, it knows, okay, this is the end of this, let's call it introduction just for the time being. And the real data will now follow. Now, to use the correct terminology, the first 56 bits of this is known as a preamble. So there's a preamble 56 bits that have the pattern 1 0 1 0 throughout, and then the final 8 bits are known as the start of frame delimiter. So that's the one that will be 1 0 1 0 1 0 1 1 to indicate exactly where this frame starts. Now, once the frame is started, it uses known field lengths, and in at least one version of Ethernet, the one that we'll be talking about, it tells you how long the content, the payload will be, and because it tells you how long the payload will be, you know exactly where it will end. So there's no need for you to have something at the end of the payload. Here we have the Ethernet frame, or more specifically, the IEEE 802.3 version of the Ethernet frame. This picture was downloaded from Wikipedia because we don't have the funds to buy the original from the IEEE. First heading that you will see is that of layer, and as you would expect, it talks about layer 2. However, it also talks about layer 1. Now, when we talk about Ethernet, we generally talk about it as a layer 2 standard. But Ethernet does indeed speak about topics such as electricity and so on. So there is indeed a physical layer of Ethernet 2. We won't be looking at that in any detail whatsoever. We'll be looking at the layer 2 specification. So as expected, you will see that there are 7 octets that function as a preamble, the 1010 pattern. Then there's your 1 octet start of frame delimiter, that's 1010, and then at the final bit position 1, so it indicates to you that this is going to be the start of the frame. And then the first entry in this is the MAC destination, 6 octets. So you can see that it is using known field lengths. It knows that this address will consist of 6 octets. This is the destination address, and more specifically the MAC, the Media Access Control destination address. We'll say more about this in a moment. Then you will also see the MAC source address, and again a known field length, 6 octets. Then there's an optional field, leave it up to you to figure out whether, or how does it know whether you've used it or not. And then there is the length that we mentioned previously. Now, one little word of warning again, you see that this length is true for the IEEE 802.3 standard, but not for Ethernet 2 type. So the Ethernet 2 is another version of Ethernet which does not include the length, and I'll leave it up to you how it will figure out where that frame ends if it doesn't know the length. Then there is the payload, which consists of 46 to 1500 octets. Why does it start at 46 and not at 1? That's something we'll have to discuss in the next video. However, note that if you're going to send 1 byte, it will have to pad it with 45 bytes of junk there to get the minimum size. Also note that there's a maximum length. And when we spoke about IP fragmentation, we said IP fragmentation is necessary when an IP packet cannot fit into the space allocated in a lower layer protocol. Now, if you have let's say about a 4 kilobyte IP packet and you have to fit it into Ethernet on layer 2, then you will have to cut it up into about 1500 block or byte chunks in able to fit it in. So this is one of the explanations why you need the ability to fragment IP, to fit it into payload fields that have a maximum length. Then, in essence, finally, you see that 4 octets are used as a CRC value, so you can check the integrity. And then it tells you that before you're allowed to send the next packet, you have to leave a gap of at least 12 octets, maybe more. Doesn't have to be anything following immediately after 12 octets. If no one wants to send anything, it can wait indefinitely until someone wants to send something. So that is just a minimum specification in terms of the internet or interpacket gap. While looking at the Ethernet frame, we encountered the notion of a MAC address, or Media Access Control address. Remember that it consisted out of 48 bits, 48-bit field, or if you want to, 6 octets. A MAC address originated in the world of 802.3, in the world of Ethernet. but it nowadays applies to all 802 protocols and related protocols. So when we talk about token ring and Bluetooth and Wi-Fi, it also applies in those cases. So the Ethernet or the MAC address consists of two fields. The one field is commonly known as the vendor code, the vendor number, the vendor ID. In other words, it refers to the organization who manufactures and supplies this piece of network equipment. Sometimes, I think in the official documentation, it talks about an organizational unique identifier. I've not seen that used in common language or in common use. The vendor code is much more commonly used. The lower half is used to indicate the network interface. Just now, we'll change that abbreviation a little bit. Logic behind an address such as this is that anyone who wants to manufacture network interface cards will acquire a vendor code. For many, many years now, it's been administered by the IEEE, and you obtain your vendor ID from the IEEE. Once you have your vendor ID, in other words, you have these 24 bits, you can begin to manufacture cards, and then you can just number them. Number 1, number 2, number 3, and so on. And because you have 24 bits or 3 octets there, you can essentially manufacture 16 million cards. If you've manufactured 16 million of these network cards, then you go back to the IEEE and you ask for another vendor code, and you can manufacture another 16 million cards. In days gone by, you typically had a separate network interface card that you plugged into your computer. So network interface card is the abbreviation that is usually used for the bottom or for the lower 24 bits. If you buy a modern computer or even a cell phone, it probably has many network interfaces on it. On a computer, it's not strange to have an Ethernet port, Bluetooth built-in, Wi-Fi built-in, and all of those interfaces will have their own network interface card address or network interface code number. So you will have multiple MAC addresses associated with the computer. A router that connects to, let's say, 256 possible other computers will have 256 different MAC addresses on it. Given the scheme that is employed here, it should be clear that vendors are getting unique IDs, numbers that are not assigned to anyone else. And when a vendor starts manufacturing their cards, whether it's separate cards or built onto a motherboard or whatever, they number them uniquely. And therefore, a MAC address will be unique in the world. There's no obvious, there's no one else who will manufacture a card with the same number as anyone else. There's a slight exception to that. Normally these MAC addresses are burnt into the hardware, but there are equipment where you can set the MAC address. And if you set it, then, or if you are able to set it, then you can set it to something that duplicates something else. The only real requirement for a MAC address is to be unique on the local area network. In other words, if you think back to this bus, this cable, then no two machines on it should have the same address, because one machine should be able to send something that another machine should pick up. So it's sent out on this medium, and all the computers that are connected to the medium will compare the destination MAC address with their own MAC address, and then if they recognize it, they will listen and take it off. So you cannot have duplicate MAC addresses on a single bus. That's the real requirement. What they ended up with, given this design, is that MAC addresses in general, apart from those couple of exceptions where you can change it in firmware, in all of those cases, you will have a globally unique address, and that's something that we saw was also used in IP version 6 to obtain an IP version 6 address that is unique worldwide. One other remark, we generally think about unicasting, sending something to a unique other station on the bus, but the scheme also makes provision for multicasting and for broadcasting. And I will let you guess what the broadcast MAC address is. Okay. It happens to be 11111, all ones. Same story that we've seen on layer 3 when we spoke about IP broadcasting. This will be broadcasting on this shared bus, or if we are talking about the other topologies, it will be broadcast on the ring or whatever other topology may be used. Now that we've introduced MAC addresses, we can take the opportunity to quickly talk about another protocol that we have to discuss somewhere, but that is hard to slot in anywhere. After we've talked about that protocol, we will return to the main topic of this video, namely data delineation. The protocol that we have to talk about is ARP, the Address Resolution Protocol. The problem is the following. Suppose a router gets a packet and it sees the IP address destination of that packet. And suppose this router knows that this IP or this IP address, the destination address, is somewhere on this bus that is connected to the router. So it has to simply put this on the wire, and it will then flow through this wire to get to the destination address. How does it figure out what the MAC address is so that it can put it on the wire such that the destination machine can see it on the wire and read it from the wire? And the answer is we'll use the ARP protocol, the Address Resolution Protocol. The ARP protocol essentially works as follows. This router that has to send a packet to some destination on this bus will send out a broadcast message on the bus. To do that, it will use the broadcast MAC address, that 11111 that we talked about. We'll send it out and it will say, I want to know the MAC address of this particular IP address. So since it's a broadcast message, it will go to every machine on that bus. Every machine will get it. They will all look at what they got and they will say, is this my IP address? And if it is, then they will respond and say, here's my MAC address. I'm the one you're looking for. If they look at it and say, no, that's not me, they'll just remain quiet. And we will very, very soon look at a couple of examples where you will see that these messages are broadcast all the time. In Wireshark, they have the form who has, and then some specific IP address, and then it will continue with it and say, tell the machine who is looking for this address. So this is a translation mechanism, sort of translating addresses between layer 2 and 3, translating it from the IP address to the MAC address once you know that you've reached the local area network or that local bus or local ring where the message is to be delivered. To make this somewhat more concrete, let's quickly play a little bit with this notion of MAC addresses and the ARP protocol. What I'm going to do, I am working on a Linux computer in this case, and if I simply say ifconfig, I will get information about all my interfaces. And one of the interfaces that you will see that is listed here is Ethernet 0, and I specifically have the hardware address listed there. If you look at the loopback address at the bottom, you will see that there's no hardware address, so it sort of makes sense that there's no hardware address. One thing about the notation that you are seeing here is on this particular computer, it separates the octets, the 6 octets, with colons. It can also separate the 6 octets with hyphens or spaces. There is no really right notation, right way of doing it, and different machines do it in different ways. So be ready to translate this in some cases, change colons to hyphens and so on. Given that hardware address, we can begin to ask if we can determine who the vendor is. So I'm going to copy that hardware address, and we will use that in a moment or two. Let us use the ARP command just to illustrate how it is used. Now, when I say we use the ARP command, there is a command built into more or less every operating system that is called ARP, and it can provide you with information about the address resolution protocols functioning on this system. The way that ARP is really used as a protocol is as a low-level mechanism in the routing algorithm. So this just gives us some additional information. What you can do is you can say ARP help, and that will show you the options that are available. You can also look at the manual page for ARP, and that will give you more information. But the most common way in which we use it is to say ARP-A. In other words, which machines has this machine been talking to recently? Because once it has translated an IP address to a MAC address, it caches it for a while. I can also use the ARP command to clear that cache, by the way. But if I want to see which machines have talked to this particular machine recently, and those are machines that share the same local area network, not global machines out there, then you will see that this computer has actually been talking to quite a number of machines in the recent past. You can see the various IP addresses, you can see the various MAC addresses, and you can also see the interface that was used to talk to those machines, to make contact with those machines. Let's now address the question that we raised a moment ago. How do I determine who manufactured a specific network card? And given the fact that so many network cards are nowadays built into the hardware, very often it will tell us who built that computer. To do that, you can simply Google ARP vendor code or something like that, and you will get a lot of machines that will provide you with that facility to look up the vendor code. This is one that I found through Google. I don't know whether it's a good one. I don't recommend it. I don't not recommend it. I'm simply going to use it, and I'm going to enter that ARP address that we got from my computer that we visited a little bit earlier, and going to ask it who manufactured that one, and you can see that the vendor in this case is Gigabyte Technology, and that computer indeed does have a Gigabyte motherboard in it. It's a computer that I built on my own, but I used a gigabyte motherboard, and this therefore correctly determined the manufacturer of that specific computer. For the sake of illustration, there are many tools that help you to do calculations and lookups in the field of networking. The app that I'm looking at this moment is one that is called Landroid. It's one that I've mentioned before. Works on Android. I assume there are iOS variants of similar apps available. I also assume there are other apps available on Android that will also do what this tool can do. What you can see as we're scrolling through it is that many of the things that we've played with, such as ping and traceroute and whois, are all available. There you can see the ARP cache. In other words, who spoke to or which machines connected to this phone via a direct connection recently. The one that I want to look at now, because it deals with the topic we are talking about, is MAC lookup. There you can enter the MAC address. What I've done is I've copied and pasted the address that we used earlier so that you don't have to wait for me to type it in. And I can now say go. It does a lookup, and what you can see there is that once again we get gigabyte as the response. I'm going to capture some traffic with Wireshark. The reason is twofold. I want to look at those ARP requests that we spoke about just now, and I also want to look at the Ethernet frame in a bit of detail. So you can see a lot of traffic running across the screen at the moment. Those yellow brownish ones are ARP requests, so quite a couple of them going through. And then a lot of UDP traffic that I see. I'm going to filter this so that I can only see the ARP requests, and you can see them going through the system. And let's stop it there so that we can explore this in a bit more detail. One of the interesting things is if you look at the source address, that is a MAC address that you expect to see there. But what you do see is that the name of the that the MAC address has been changed into a vendor name and then a network interface card number. So ASRock is the vendor of that first packet, and the specific network interface card on that happens to be number 29D33E. That machine seemed to have been fairly busy. The destination, as we would expect, is always a broadcast. And you can see the typical question, who has a particular IP address, and then whom should be informed about this. If we open what's been captured, then you can see on the highest layer, in other words, the bottommost packet, the innermost packet, that this is an ARP request, and we are asking for an IP version 4 address. The sender MAC address is specified there as ASRock, and the network interface card number is specified there. You can always also see in brackets that it gives you the vendor code in hexadecimal. For any given company, they will probably have more than one vendor code, so that one happens to belong to ASRock, but I wouldn't be surprised if ASRock has a number of vendor IDs. And then the target IP address, what is it looking for? What does it want to have resolved? So pretty simple, and you can see that I am indeed seeing a lot of those requests on my network. If we look at the Ethernet frame, then what is interesting immediately is that this is an Ethernet 2 frame. Recall from our discussion of the Ethernet frame that we looked at the 802.3 Ethernet frame, which had a length of the payload in it, and Ethernet 2 did not have a length in there. So in terms of Ethernet 2, the question was indeed, how do you determine the length? Now, you can see there in the uppermost line that it captured 60 bytes on the wire, 480 bits. But how did it know how that it should capture so many? Leaving that as a question for you to consider. Destination of this Ethernet frame is broadcast. So there is the MAC broadcast address, FFFF, and so on, as we would have expected. And then the source address, the payload is ARP, and there is some padding. This, again, typical of what you should do. Obviously, you will be getting Ethernet frames for basically every type of traffic you capture, not only ARP, so you should also go and look at those. Question to think about for a moment or two: on which layer does ARP belong? Because ARP deals with layer 3 issues. It wants to not resolve, it rather wants to find a MAC or find an IP address, a layer 3 address, and then it wants to translate that into a layer 2 address. So in a sense, it is something that binds layer 2 and 3 together, doesn't really operate on layer 2, doesn't really operate on layer 3. Perhaps we should think of it as a layer 2.5 protocol. The final protocol for which we will discuss data delineation is the token ring protocol that was originally designed by IBM, so often it's referred to as IBM token ring, but it was also standardized by the IEEE as IEEE 802.5. The token ring protocol uses a very, very interesting technique to delineate its data. But unfortunately, to look at it, we have to go down to layer 1 once again and look at some physical characteristics. And we'll do that in a moment or two. What we're just going to do before we do that is to look at the frames that are available in token ring, because there are quite a couple of frames available. And then we will look at the nice trick that they used in this protocol to delineate data. Here we have the Wikipedia page that shows us the various frames that are used in token ring. Once again, we don't have funds to buy the original IEEE document, so Wikipedia will have to do. What you will see on this page is that there are a number of frames that are in use. For example, the very first one that is listed, more or less at the top of the screen, is a token. So a token is a special type of frame, and you can see that it consists of a start delimiter, some access control bits, and an end delimiter. How those access control bits work are not important for our purposes right now. There's also an abort frame, and then the next one that is arguably the one that we should spend most time discussing is the data frame, the one that is used to carry data. And you can see that starts with a start delimiter, access control, and then various other fields, and eventually you also have the actual data, a CRC, and some markers at the end of the data again to delineate it. So clearly what is used here is a mark at the beginning and a mark at the end. And the mark at the beginning looks, as you can see on the screen there, it contains a J and a K, and that's where the trick lies. So that's what we have to discuss in more detail. Then just a normal 0, and then another J and another K. Again, that's the trick that we have to look at. And then it contains a couple of zeros. There's the access control part that we're not going to look at, but we are very briefly also going to look at the ending delimiter, the one that you use at the end of the frame to indicate where it ends. And there you once again see those unusual J and K values, and then a 1, a J, a K, a 1, and then 2 other values that are not interesting for us right now. So the secret of data delineation here is or lies in those J's and K's. Here we have a picture of data encoding that we have once again grabbed from Wikipedia. Just a simple indication of how data may be encoded, and we are in particular interested in Manchester encoding. What you can see here is a clock value, and then we have our data value. Now, often data is encoded exactly in the way in which you see it represented there. That is in a code that is typically referred to as non-return to 0. So on an electrical level, it may mean that you are transmitting 0 volts there and 5 volts there and 0 volts there and 5 volts there and so on. So high voltage and a low voltage for a 1 and a 0, or even vice versa. The point is that in some schemes you will encode data in exactly that way. Here is one of those examples of why data communications is often so confusing. Because here you will see 2 examples of Manchester. If you look at the 2, you will see that they are essentially mirror images of one another. So let's look at the IEEE version. What you will see, and it's not clearly indicated on this first byte boundary, is that we have byte boundaries. And the really important thing to note here is that with NRZ, the signal values only changed on the byte boundaries. In that case, it didn't change because we had 2 identical bits. There also it did not change because we had 3 identical bits following one another. However, what you see with Manchester is that in the middle of every bit interval, there's a transition. So it doesn't matter whether you are transmitting a 0 or a 1, in the middle there will be a transition. Note the ones that I've skipped here. Those are not 1s and 0s, those are just markers, little markers that I'm adding there, are transitions that are on byte boundaries. What this tells us is if you use the 802.3 convention, a low high is a 1. So if you find there's a 1, if you look at the other one here, then there's again a low high. If you find the other one there, there is again a low high in that bit interval, and then the same for the final ones, a low and high. On the other hand, the zeros are a high, low, high, low, high, low. And then sometimes, because the previous byte bit ended on a low and the next one starts at a high, you have to transition on a byte boundary. So that's the reason why you have those transitions on the byte boundaries, just to get to the right starting point. So the reason or the logic of this encoding scheme is that as you are transmitting the data, there is a transition in the middle of every bit interval. So if you are transmitting a long sequence of zeros or a long sequence of ones, There, for example, we had a long sequence of ones that were transmitted. Only 3 is not that long, but if you're transmitting 50 ones, then your clock may drift and you may think that you've seen 51 or 49 ones. Here, because you have a transition in the middle of every bit interval, you can, number one, make sure that you see that transition, so you won't double count or undercount. But number two, you can also adjust your clock. If the middle of the bit transition comes too early, then it means you have to change the speed of your clock so that you expect the middle of the transition or middle of bit transitions earlier. Or if it comes too late, same thing, you have to adjust your clock to run at a slightly different speed. Now, in a sense, law in Manchester encoding is that you have a transition in the middle of every bit interval. The trick that tokering uses to delineate data is to use a start delimiter that looks as follows: JK0, JK000. Similarly, it uses an end delimiter that is JK1, JK1, and then 2 special bits that we are ignoring for the time being. So the J's will be encoded as follows. If we get our bit boundaries denoted so that we can keep track of where we are, then the J will be a coding violation in the sense that it will be a low. There won't be any transition in the middle of the bit interval. The K will be a coding violation in the sense that there will be a high. No transition in the middle. And then the 0 will be a normal 0. If we use the 802.3 convention, it will look like that. Then the J will again be a coding violation, no transition in the middle. The K will again be a coding violation, no transition in the middle. And then the remaining zeros will be encoded exactly like other normal zeros. No problem, transition in the middle as expected. So I've drawn this sort of as isolated little lines. The signal will of course be continuous, so it will look like that. Again, transition on the boundary, and then from there on the remaining zeros. Now, what we've done here by introducing these coding violations, these are not legal data, they're not valid data, and therefore there's no way that they can occur inside any data. And because they cannot appear inside any data, they are unique in the sense that they can only be used in these very special positions to delineate data. While we didn't spend time discussing it, you may have seen that known field lengths were used for most of the fields in the data frames in a token ring. The only part that can vary in length is the payload, the actual data that is being carried, but that is handled because we have an end of frame delimiter, end of data delimiter that is in place to indicate where it ends. As we've said on a number of occasions now, when we talk about the data link layer, we are thinking about 3 concepts: error control, which we discussed in the first 2 videos, data delineation, which we discussed in this video, and then access control or media access control, also referred to as contention control, which will be the topic of the final 2 videos in the series on the data link layer. See you soon.